Hi, I'm Hsin-Ping, a master's student from National Tsinghua University. Today, I'm gonna present Reblanced Mixup, a regularization technique for imbalanced data. This is a joint work with my supervisor, Professor Shih-Chieh, and collaborators Jia-Yu, Wei, Da-Cheng from Google Research. I want to first show why imbalanced data is an important problem for image classification. It has been shown in previous studies that real-world images naturally exhibit such long-tail distribution. In many real-world image classification applications, it is extremely hard to avoid such imbalance when constructing datasets. Unfortunately, when convolutional neural networks are trained on these class imbalanced datasets, it often leads to poor generalization. Specifically, convolutional neural networks will struggle classifying the minority class images. For example, suppose we have many images from the class yellow plant, but we have very few images from the class butterfly. After training on such dataset, the classifier is able to accurately classify yellow plant images, but fails to classify butterfly images. To solve the imbalance problem for large-scale image classification, we have studied previous works to this problem and realized we need a solution that is computation efficient, end-to-end trainable, easy to integrate, and of course, a solution that provides better performance. These goals are critical because the current solutions of imbalance problem often rely on sophisticated way to generate minority samples or decoupling the neural networks into different parts and train them separately, which increase additional effort for training the model. To achieve the goals, the first thing that came to our mind which qualified all these properties was regularization. We then surveyed the state-of-the-art regularization techniques on balanced datasets. A special but easy regularization drew our attention, and that is Mixup. Despite Mixup's significant improvement on balanced datasets, we empirically found that it does not bring as much improvement on imbalanced datasets as it does on balanced datasets. As a result, I'm gonna talk about how we redesign Mixup into Remix so that it can be more suitable for the problem of imbalanced data. Let's first briefly go through Mixup. Mixup is a simple regularization which proposes to train the neural networks on linear combinations of images and their corresponding one-hot labels. Every training iteration, a mixing factor lambda will be sampled from the beta distribution, and the two different batches of images and their corresponding labels will be mixed using this mixing factor lambda. As I said before, since it was originally designed for balanced datasets and does not take the imbalance into consideration, Mixup isn't very effective on imbalanced datasets. Thus, it raises a question: how can we modify Mixup for imbalanced data? The answer is we can integrate a common consensus for solving imbalanced data into the Mixup regularization, which is integrating the trade-off between majority class and the minority class. Recent studies show that in order to improve generalization, we can push the decision boundary towards the majority class. By doing so, the classifier learns to treat the minority class less strict and gain better performance. Note that this is a trade-off between the majority class and the minority class. So it is also important that we can control how much we want to move the decision boundary so that we won't significantly hurt the performance of the majority class. Now we know that pushing the decision boundary towards the majority class may improve the performance. Then the next question is how? How can we move the decision boundary using Mixup? We first look at the decision boundary of Mixup. Suppose we are using Mixup on a linear max margin classifier, then the decision boundary should lie in the middle. If we want to push the decision boundary towards the majority class, we can label the mixed image as 100% the minority class and do the same for all the mixed samples in the right of this point. This is very different from traditional oversampling techniques because these mixed samples actually involve both the features of the majority class and the minority class. Yet, we mark the labels of these mixed samples as 100% the minority class. Learning on these samples guides the classifier to make predictions in favor to the minority class when it finds both kinds of features in presence. And yeah, that's pretty much the core idea of remix. Now we know how we can move the decision boundary. The next question is, how can we control the extent we want to move it? The answer is quite simple as well. We can control the exact point that we start labeling the mixed samples as 100% the minority class. Let's look at an illustration of the concept. We designed a hyperparameter tau to control the movement. In figure C, when every mixed sample on the dashed line is labeled as 100% the minority class, the decision boundary will look like this. As we gradually decrease the value of tau, the decision boundary will move towards the middle. Let's see how we can formulate the high-level idea into equations. Note that unlike mix-up, we allow the feature space and label space to have different mixing factors, lambda x and lambda y. Lambda x is sample from beta distribution just like mix-up, and lambda y will be determined using the below function. It might seem a little bit complex, but the goal is really simple. When the mixing is conducted between two classes that their imbalance ratio is larger than the threshold kappa, then we want to label the mixed samples as 100% the minority class from the starting point, tau. Otherwise, it would set lambda y equal to lambda x, so that remix would degenerate into mix-up. The step-by-step algorithm will be like this. For every training iteration, we will sample lambda x from the beta distribution as the mixing factor, and mix the two batches of images according to the mixing factor. Then for every mixed images, we generate their corresponding lambda y so that we can label the mixed images as we have explained previously. And the rest part is just simple SGD algorithm. To provide an intuitive explanation for the success of remix, we visualize the decision boundary on a toy dataset, the 2-moon dataset from scikit-learn. Note that remix has performed as we expected. The decision boundary is pushed towards the majority class, and thus more minority samples are being accurately classified. We highlight the key difference using the yellow circles. We have also conducted experiments on various imbalance ratios and imbalance types on imbalance datasets. Here we show the experimental results on imbalance cipher. Remix not only significantly improved mix-up when it is used with reweighting or resampling techniques, it outperforms previous state-of-the-arts. Here we show another experimental result on a large-scale datasets iNaturalist 2018. Note that our method again achieves superior performance. To conclude, we propose a regularization technique, remix, to solve the imbalance problem in image classification. Remix is computation efficient, end-to-end trainable, and easy to implement or integrate with existing methods. All these advantages make remix easier to deploy on large-scale datasets compared to previous methods. For more experimental results and other details regarding our method, please refer to our paper and supplementary material. Thank you for watching.